Today we're going to address the concept of uncertainty and how we can use it together with expectation values to characterize the spin of a quantum system. So for example, one way that we can do this is by writing down the state vector or the wave function of the state itself. For example, like this. This contains all the information that there is about the system spin. We haven't left anything out at all, and we could compute anything we want to know about any possible measurement that we could do based off of this. But oftentimes, all we care about is the expected behavior of a system in relation to a particular measurement or set of measurements. We could specify that measurement of spin in some direction. We'll have values of plus or minus h bar over 2 with probabilities of p and 1 minus p. But that's a bit of a mouthful, and it can still be a lot to work with. Instead, what we usually do is we break this down into the expectation value, right, the average result of measurements made on many identical systems, as well as another number that quantifies how much individual measurements tend to vary from the expectation value or mean. The most general term for this concept is called an uncertainty, and the most common way of computing or describing uncertainties is through the standard deviation. I should emphasize that these three methods of characterizing a system spin are not all equal. The first one, the state vector itself, contains everything there is to know about a system. But even in this second one, we've given up some information. It tells us if I were to make a measurement to spin along some particular axis, I would get h bar over 2 or minus h bar over 2 with given certain probabilities. But I've lost information about the phase of my amplitudes in this process because to get the probabilities, I square them, their magnitudes. And so what I've also lost is the ability to make good predictions about the outcome of measuring spin in a different direction. So we've lost some information going from 1 to 2. We've also lost some information going from 2 to 3 because while I know the average and I know the uncertainty, which tells me kind of the tendency of individual measurements to deviate from that average, it doesn't tell me how much each individual measurement will deviate. It gives us a trend. In the case of a spin 1/2 system like the ones that we deal with, it turns out it basically gives us all the information that there is because there are only two options for the values of the measurement. So we can use the context of the fact that we know some information about spin in general to narrow down what the uncertainty means. But generally speaking, even going from 2 to 3, we lose some information. However, 3 is helpful because it's easy to quantify. I can easily measure an average and I can easily compute a standard deviation, and these two numbers together let me quantify a measurement in a nice simple way that I can easily compare to an experiment, to another experiment, or to a theory. So again, we have lost information getting here, but it's usually enough and it's much easier to compare things using this third method than the other two. So what is a standard deviation? Well, most or maybe all of you have learned about standard deviations in the past, but I'm not sure how long ago it was, and I don't know exactly what form of the equations you've been given for it. In this course, we're going to use a mathematical formulation of the standard deviation that's particularly well suited to this concept of operators. It lets us define the standard deviation in terms of operators and expectation values. So we're going to define our standard deviation as the square root of the average of the measurement squared minus the square of the average value. Delta S is the standard way of expressing an uncertainty or standard deviation. In this case, what it means is the standard deviation of a measurement S on a state psi. On the right, we see the average value or expectation value of S, quantity squared. And the term in the middle doesn't really have its own name. But again, first we're squaring our measurement, and then we're taking the average of all of our squared values. In terms of operators, we can calculate this in basically the same way we do the expectation value, which is why we use almost the same notation for it. These brackets mean that this operator squared is being sandwiched between the bra and ket of our state psi. The squared operator simply means take the matrix form of the operator and multiply it by itself. The quantity under the square root does have a name as a whole. It's called the variance. The variance is basically, again, it's what we're looking for. It's a measure of to what extent our individual or our individual values tend to differ from the average value. For example, if you consider two numbers, 1 and -1, their average value is 0. But their average squared value is 1 because 1 squared is 1 and -1 squared is 1, and the average of 1 and 1 is 1. And so this gives us a standard deviation of 1 minus 0 under the square root, which gives us 1. And so our average value is a 0, and our standard deviation is a 1, and that tells us that the average value is 0, and our individual values tend to differ from 0 by an amount of 1. It doesn't specify the direction they tend to differ because it can go up or down. And so that's why we're first squaring it. This tells us the sort of size of our number, and this tells us the average of our number. And the difference of those is a way that we can use to quantify the expected difference between a particular number and the average. Now, I haven't explicitly justified that this, in fact, is what I described it as. But if you think back to the previous video on expectation values, I did show that by sandwiching an operator in between the bra and the ket of a particular state, it outputs the average result of that operator weighted by the probability of each possible output. And S squared is simply a new operator. S is a spin operator, and S squared is the operator you get by multiplying the spin operator times itself. You can think of this as two successive measurements, if you'd like, measuring the spin and then measuring the spin again. It's a little bit more complex than that, but that's the general gist. Again, putting any operator in between a bra and a ket of the same state is going to give you the average, the weighted average by probability of the possible results of that particular operation. Let's do a couple examples, and let's start with the simple one so that we can actually verify that the result makes sense. So, for example, let's consider some initial state that's just z plus. Keep it simple. What I want to do is I want to calculate the standard deviation of the operator sz on the state z plus. In other words, what is the uncertainty of the spin in the z direction of a state that is z plus? Hopefully you can answer that already, but let's actually do the math to confirm that the math tells us what we think we should get. First, recall the matrix form of the SC operator, which is h bar over 2 with a 1 and minus 1 along the main diagonal. Next, we can compute the expectation value, which gives us positive h bar over 2. So far, this shouldn't be surprising. A state that is just z plus has a 100% chance of being measured to have a positive h bar over 2 spin, and so the average value should be positive h bar over 2. The next step is to compute the expectation value of SZ squared. So we do the same thing, except instead of having SZ in here, we have SZ in there twice. Now, a fun little thing to notice is if you multiply the SZ operator by itself, you get a factor of h bar squared over 4 times the identity matrix. The matrix 1, 0, 0, minus 1 times itself gives us the identity. And so this is actually pretty straightforward to compute. We find that the expectation value of SC squared is simply h bar over 2 quantity squared, which is not so surprising. It's simply the square of what we got the first time. That is not always the case. It is the case this time, but it won't always be that way. We'll see an example in a bit. Now we're ready to plug these back into the equation for the standard deviation or the uncertainty, and we find the square root of h bar over 2 quantity squared minus h bar over 2 squared, and that's just equal to 0. So what does that mean? Why is it equal to 0? Well, we should have been able to guess that it would be equal to 0 because, as we already established, a state that's directly proportional to, for example, z plus, it is what we call a well-defined spin state. It has a well-defined value of spin in the z direction, and every time I measure spin in the z direction, I will always get the same value, h bar over 2, positive. And of course, if I always get the same value every time I perform a measurement, there is no uncertainty. The way that we typically write this is by writing as the expectation value plus or minus the uncertainty. This is simply a nice concise notation to describe sort of the character of our system. It has an average value of spin given by this, and the individual measurements performed tend to vary by about this much. It doesn't necessarily mean that they vary by exactly this much. Sometimes you might get a bigger variation. Sometimes you'll get a smaller variation. But again, this is talking about trends. This is the statistics of a large number of measurements. So again, we have lost some information here. We don't have all the information that we would have if we still stuck with the actual wave function. But in practice, this is often more convenient, especially when it comes to actually doing experiments and making measurements and doing things in the real world. Because in the real world, I can't measure the wave function. The wave function cannot be directly probed by any kind of experiment. All we can do is measure outcomes, and through repetition, we can determine the probability of those outcomes. And together, those two things allow us to compute averages and uncertainties. And so usually, we take our wave function from our theory, and we compute the expectation value and the uncertainty in order to be able to compare it to the real world experiments that we do. Let's do one more example, one that's a little bit less simple than this one. And then we'll move on to a discussion on what uncertainty really is and how it's different in quantum mechanics versus in classical mechanics or in really the other sciences in general. So here I want to find the uncertainty of spin in the x direction of the given state psi. So I do this the same way as before. I have the square root of my variance, and we should start by simply calculating the expectation value of Sx for the state psi, and the expectation value for the spin x operator squared for the same state psi. First thing to note is recall that the matrix form of Sx is h bar over 2 with 1s on the off diagonals. This allows us to compute the expectation value the same way as before. It's messier. Don't forget the minus sign right here. Remember, this is the ket for psi. When I write down the bra, I have to complex conjugate all of the amplitudes. So anywhere you have an I, you have to flip the sign. So I have a negative sign right here because this is the bra vector, and I have a positive sign right here because this is the ket vector that I defined originally. Be careful of that. It's something that's really easy to forget or to miss. So if we continue working through it, you could, again, either choose to multiply this row vector onto this matrix, right? So one row times a column gives you the first row, first column. Then row times the second column gives you first row, second column. Then you'd have a row vector times a column vector. I don't know why, but I personally prefer first multiplying the matrix here onto the vector over here, and then always going from the left. It doesn't really matter which way you do. For some reason, this is just the way I always do it, and I feel uncomfortable doing it any other way. Although sometimes there are reasons to do it the other way, but I'm going to do it my way. And if you do this last step, you will pretty quickly find that it's equal to 0. So the expectation value of spin in the x direction of this particular state is equal to 0. Now the reason for that is that I put this I here. You'll notice that this is kind of reminiscent of a state with a spin in the y direction. So this state kind of has like a combination of spins in the z and in the y direction with no average spin in the x direction. If I took out this I, the expectation value here would not have been 0 because this negative sign would be positive, the I would be gone, and things would add instead of subtract. And this state would have an expectation value in the x direction, a non-zero expectation value in the z direction, but it would have a 0 expectation value in the y direction. Anyways, that's a bit of a tangent. but you can qualitatively analyze the behavior of some of these states once you get used to their features. The next step is, again, to compute then the expectation value of the operator, the spin operator squared. And again, all we do is we multiply Sx by itself. Now, last time we saw that Sz times itself gave us h bar over 2 squared times the identity. And if you multiply Sx by itself, you'll find you get the same thing. And in fact, that is true for all of them. Sx squared is equal to Sy squared is equal to Sz squared. They're all equal to the identity matrix times h bar over 2 squared. That makes this nice and simple. This pretty quickly ends up being simple multiplication of this row by this column with this stuff out front. And we end up with 3/8 h bar squared. Now what we do is we plug back into the equation for standard deviation, and we have the square root of 3/8 h bar squared minus 0, which gives us square root of 3/8 times h bar. Now, one thing that we can always do is the uncertainty of spin for a spin 1/2 particle like an electron, like what we've been talking about, where spin is either plus or minus h bar over 2, the uncertainty will always be less than or equal to h bar over 2. It can never be more than that. If you think about it, if the expectation value or average value is 0, that means that half the time the spin is plus h bar over 2 and half the time it's minus h bar over 2. So its uncertainty would be plus h bar over 2. The actual measurements differ from the mean by h bar over 2 exactly, and so the standard deviation would reflect that. If the expectation value is not 0, if it's greater than 0, that does mean that sometimes the deviation will be greater than h bar over 2, right? If the expectation value is a little bit greater than 0, then whenever you measure minus h bar over 2, that's a bigger deviation from h bar over 2. But more often, you're actually measuring plus h bar over 2 because the average is positive. And so mostly you're getting a smaller deviation. And so if you're more often getting a smaller deviation than a larger one by the same amount, then the standard deviation is going to actually be a little bit smaller. So what you can always do is you can verify that your work does indeed result in an uncertainty that is less than or equal to h bar over 2. For example, in a couple places in the previous few minutes, you may have noticed that there are some weird cuts, and that's because I screwed up my math. I forgot to square the 2 in the denominator, and I got an uncertainty of h bar over the square root of 3, which is greater than h bar over 2. And I didn't catch it when I wrote my notes, and I caught it just right now when I made the video. So this can be a useful thing to be aware of. What I want to do now is talk about what is uncertainty. Well, the classic understanding of uncertainty is very experimental. It's something you've been doing for years in your science labs, right? Every time you do your error analysis, you're qualitatively analyzing the uncertainties inherent to your experiment. What you're saying is that the tools and the methods you're using to measure your results are imperfect, and so therefore the numbers that you get are not precise. You don't know for a fact that the numbers you recorded are completely reflective of the system you measured. And so that's the traditional understanding of what uncertainty is. It is the understanding that our measurements themselves are imperfect, and as a result, our data is imperfect, and as a result, our conclusions are imperfect. And uncertainty is a method of mathematically quantifying that. It allows us to say, I have an expectation value, I have an average value of my data given by this number, but based off of the flaws in my experiment, I expect that the actual value that I was looking for falls within some range around my expectation value that's determined by the uncertainty. And again, the standard deviation is the usual method of doing this. It's not the only way of expressing uncertainty. It also doesn't mean that we are completely 100% sure that the actual answer falls within that range. For example, in the example that I've drawn here, right, my expectation value is 450,000. My what we call error bars representing my range of uncertainty is fairly large because I'm not very well suited to this particular experiment or measurement. But But the standard deviation specifically means that approximately 66%, there's like a 66% chance that the actual value lies within this range. I could go for a second standard deviation, which would make my range a little bit bigger, and that would increase my probability, I don't remember what the number is, to a greater number that the actual value lies within that range, and so on. So when you see error bars on a graph, you shouldn't think, oh, okay, that means the actual value is somewhere within that range. No, it means unless the error bars are specified as something other than a standard deviation, that there's about a 2/3 chance that the actual value lies within that range. And it is, in fact, the case that the farther you get out of that range, the less and less likely the actual value is likely to be found. So this is what uncertainty really is typically used to mean. It's used to relate the flaws in our experiments to the conclusions that we draw from them, and it allows us to quantify how certain we are in our conclusions. So if you ever hear something is like, in physics, a standard of discovery in a lot of fields, for example, is what we call 5 sigma, where sigma represents one standard deviation. A 5 sigma measurement means that we are confident to within 5 standard deviations that the measured result is not a result of randomness or noise or something like that. 5 sigma means there's something like 1 in a billion chance that the result we see is sort of accidental. Obviously, this doesn't account for flaws that we are not aware of. If we do an experiment and we're not aware of a flaw, we cannot account for it. And so a really major component of all scientific research is a very careful accounting of all of the possible ways in which your system can be imprecise, or inaccurate, whether randomly or systematically. But the uncertainty that we've been talking about in the first 2/3 of this video, more than that, is not this. This is classical uncertainty. It is the uncertainty of our results based off of the flaws in our experiments. But the uncertainty that we were just talking about are not uncertainties of experiments. They are uncertainties of physical states. At no point in our earlier calculations did I ever talk about how we were measuring something, about the limitations of our measurements. All of those computations were done based solely on the physical state we were working with. And we started with the wave function itself. We started with 100% of the information there is to have. We started with all the information there is, and yet there was uncertainty. And so the uncertainty that we are dealing with here in quantum mechanics in general is an intrinsic uncertainty to the nature of reality itself. A particle is described, is modeled by its wave function. Its wave function tells us everything, or describes everything there is about that state. And yet, that leaves room for uncertainty, because when you actually perform a measurement, even if you perform a perfect measurement with no flaws whatsoever, there is no way of knowing exactly what you'll get. There is a randomness associated to quantum mechanics that is not present in classical physics or in most of the other sciences. So to recap a little bit, sort of the classical uncertainty is the notion that imperfect measurements yield imperfect information about a system, which means that the results we conclude are uncertain. We cannot be positive that the actual value we ended up with is the right value, and so we use uncertainty to quantify sort of the range in which we expect the real value to actually lie. It is a consequence of measurements giving us imperfect knowledge of a system. Quantum uncertainty is fundamentally different because we can start with everything there is to know about the system. We can start with perfect knowledge. If we know the wave function describing a system, we know everything there is about the system. But despite that, if I know that a state is in the state z plus and I measure spin in the x direction, I will get plus or minus h bar over 2. I know that. But I cannot predict which one I will end up with. There is this indeterminacy of quantum mechanics that we describe with the same language as uncertainty. We say that there is uncertainty in the x component of spin of this particular state. And again, not because we don't know something about the system or we made a measurement on the system that wasn't quite perfect, but because it is fundamentally unknowable, because it is fundamentally probabilistic. It is kind of unfortunate that we use the same language to refer to these two concepts because they are different, and the classical sense of uncertainty also applies to quantum mechanics. I can't perform perfect experiments in quantum mechanics either. So the system itself has an uncertainty to it that we often call quantum fuzziness, the fact that you can never predict, even with perfect information, what exactly will happen. But if I make a measurement on a system, if I try to figure out what my system is doing, my measurements aren't perfect. So I can't experimentally figure out the wave function perfectly. I can sort of figure out the wave function. The better my measurement, the better I can figure out the wave function. But ultimately, my knowledge of the system is limited by my ability to perform good measurements. And so both kinds of uncertainty apply to quantum mechanics. Quantum uncertainty gives us a lower limit. It tells us we will never be able to make a prediction better than blank. Measurement uncertainty then simply adds more uncertainty on top of that. So in order to actually investigate this quantum uncertainty, you have to get to a point where your measurement uncertainty is really, really, really small, smaller than the quantum uncertainty. Otherwise, it will drown it out. This is one of the reasons why it took so long for quantum mechanics to be discovered. We had to get good enough at making really precise measurements on really, really tiny systems, impossible to see, before this was even really noticeable. Now here's the really fun part. Is what I just explained true, or is it all a big misunderstanding? The answer is that, honestly, I don't know, and neither does anybody else. What I just explained or described is part of the standard interpretation of quantum mechanics, usually referred to as the Copenhagen interpretation, although there are some variations of it that this also applies to. The truth, though, is that quantum mechanics is, at its heart, a mathematical model. It is a series of equations with certain inputs that allows us to predict outcomes of events. Probabilistically, sure, so not perfectly, but nonetheless, that's what quantum mechanics does. It lets us quantify the probability as well. So it is not just like totally random, unpredictable. It's probabilistic, but in a sort of reasoned sense. The problem is there are actually different ways of interpreting the mathematics of quantum mechanics. And those different interpretations deal with what I just described as quantum uncertaintiness or quantum fuzziness in different ways. The standard Copenhagen interpretation and even all of its variations are consistent with everything I just told you. But if we were to investigate more sort of experimental interpretations, I'll say, certainly less conventionally accepted interpretations, then what I just said might not be entirely true. There are interpretations of quantum mechanics that are completely deterministic, like pilot wave or de Broglie-Bohm mechanics. There are other interpretations that are also deterministic, but in a totally different kind of way, like many worlds interpretation. There are objective collapse theories and all kinds of other crazy things about interpreting quantum mechanics. And so this notion of uncertainty and even the idea of what constitutes a measurement turns out to be critical to understanding the real conceptual nature of quantum mechanics. This is the origin of a lot of the quotes you've heard. If someone says they understand quantum mechanics, it means they don't understand it. It's kind of a tongue-in-cheek way. It doesn't mean, if you talk to a physicist who's been doing this for 30 years, if they say, oh yeah, they've got a handle on quantum mechanics, that they're full of it. That's not really what it means. What it means is if someone thinks that they really know what's going on under the hood, beneath the math, then they are making major unjustified assumptions. The mathematics is something we're confident about. The predictions we're confident about. But what is being physically described? Is the wave function real? Or is it simply a tool we use to model something that is real and that we just can't directly see? Is the wave function that we describe really everything? Or is there more information to be had? Are there what we call hidden variables? Turns out if there are hidden variables, that it imposes strict limitations on what else can sort of be true of the universe. And we're going to talk about all that later. But my point is, from this point on, I really want you to understand that the language and the ways that I'm using to describe things are in the conventional interpretation of quantum mechanics that we call Copenhagen interpretation. It is simple from a pedagogical sense. It is conventional, so if you look things up online or elsewhere, this is what you'll probably be faced with for the most part. And so I think it makes the most sense to introduce it from this perspective. I do want to make it clear, though, that this is not necessarily perfect information. We don't necessarily know whether the language we're using here is truly reflective of the nature of reality or whether it's merely an artifact of the mathematical model that we use to describe reality. Again, we're going to investigate this in a lot more depth going forwards. We're going to continue a little bit more with operators. We're going to then move on to uncertainty principles. And once we are done with uncertainty principles, we'll start to talk about quantum entanglement. And once we've spoken about quantum entanglement, we'll be able to investigate everything I just spoke about in a lot more detail. I don't expect you to have understood all the last several minutes of my rambling. But my point is I don't want you to look at this and I don't want you to ingrain in your brain that this is the way things absolutely must work. This is merely the way that we conventionally understand the universe, but deep down inside, we should accept that there are other possibilities. And again, we'll discuss those possibilities later. All right, see you next time.